Hello, my name is Ashutosh, and I'm here to talk about a very popular technique in atomic force microscope, which is called as electrostatic force microscope, or EFM. And this talk will provide you an overview on how to get information about electric properties of your sample surfaces using EFM. So in EFM, the electrostatic force between the tip and the sample is measured, and this electrostatic force on the tip is because of the tip sample capacitance. Generally, a voltage is applied between the tip and the sample, and the tip hovers few nanometers above the sample surface to give you a map of the electric properties of the sample surface. This right-hand side image depicts the interaction forces on the tip. And generally, we find that these interaction forces are both long-range as well as short-range forces. Since we are talking about electrostatic force, we find that this electrostatic force come under this long-range interaction force, and it comes under this non-contact regime of this interaction force versus the tip sample distance graph. There are basically two main approaches, using which we can perform an EFM experiment. The first approach exploits the tip distance dependence of electrostatic and van der Waals force by employing something called as the dual pass lift mode technique. So generally, what we find is that whenever the tip is very close to the sample surface, the van der Waals forces are dominant. However, when the tip is lifted to a certain height, then the van der Waals forces rapidly decrease, and the electrostatic force, in this case, become the dominant force. So what we generally do in this dual pass lift mode technique is that we perform two passes. So it's the first pass scan and the second pass scan. In the first pass, the tip scans the sample surface to reveal the topography where the van der Waals forces are dominant. The tip is then lifted, let's say, 50 nanometers or so away from the sample surface, all right, where the van der Waals forces are negligible now. And a second pass now is performed along the same topography lines to detect the electric properties of the sample surface at every point along the sample. So if you take a look at this figure, then this black line reveals the topography of the sample, and this is generally done in Park's true non-contact mode. Then the tip is lifted to a certain height, and then this second pass is performed along these topographical lines to reveal the electric properties of the sample surface where the electrostatic force are dominant. Then there is a second approach or a second technique, which is called as a single pass technique, which uses a different frequency for detection of the electrostatic force with respect to your topographical imaging. In this case, the van der Waals forces and the electrostatic forces are decoupled by using an additional lock-in amplifier for the EFM signal. So what happens in this single pass method is that the tip scans the surface of the sample, right, by at a resonant frequency, which is omega naught, and this is nothing but it's the cantilever resonant frequency omega naught, and this surface topography is generally mapped, using this first lock-in amplifier, okay, which locks in the surface topography signals at this cantilever resonant frequency omega naught in Park's true non-contact mode. At the same time, an AC bias, okay, at the same time an AC bias with a frequency omega tip, okay, is applied to the cantilever or the tip along with the DC bias. So what happens here is that this second lock-in amplifier now comes into picture, and the second lock-in amplifier then decouples the motion of the tip and separates the electrostatic signal from the topographical signal. And this is done at the frequency which is given by omega tip, or it is the frequency at which you apply your AC sinusoidal voltage. So if you take a look at this schematic diagram, then in this figure what we find is that there is a single pass that is performed, and in this single pass, both the topography, which is locked in at this cantilever resonant frequency omega naught, plus the EFM signal, which is locked in at a frequency which is given by omega tip, okay, is both these signals are then captured at the same time. This single pass method is superior to your lift pass, is superior to your lift mode technique, because this method gives you high spatial resolution, and it also requires less time for scanning. This is a schematic diagram of the entire setup or the experimental setup for the dual pass frequency EFM. So here we can clearly see that there is this first lock-in amplifier which locks in at this cantilever resonant frequency omega naught, all right, and this feedback loop then provides you or reveals the topography of your sample surface. Then we apply this AC voltage and this DC bias, right? And what happens here is that now there is a second lock-in amplifier which locks in at a frequency omega tip, which is the frequency of your AC sinusoidal voltage. And then this reveals or it basically decouples the electrostatic force or electrostatic signal from your topographical signal, and it reveals the map of your electric properties of the sample surface. Now, generally, what we find is that mathematically, the electrostatic force is given by this equation number 1. And whenever we talk about electrostatic force, we need to really see which voltages are involved. And generally, we find that you have the surface potential voltage, which is given by Vs, plus you apply a DC voltage, plus you apply a sinusoidal AC voltage to the tip. Okay. Now, if you take a look at this equation number 1, what we can do is we can expand this equation, and when we expand this equation, these 3 terms, right, pop up as we expand this equation number 1. Now, all these 3 terms have got their own importance, and what we can do is, very briefly, we can see each of this term. In EFM, what we can do is we can, let's say, just apply a DC voltage to the sample or to the tip. And then the electrostatic force that is measured, is given by this equation number 2, which is nothing but the first term that popped up, when you expand equation number 1. Now, since we apply only DC voltage to the tip, what we find is that this particular electrostatic force that we try to map, okay, it is only measured with respect to the static bending of the cantilever, and generally this kind of measurement derives a qualitative map of the sample potential or the surface potential of your sample surface. One example that is shown here is PET coated nanowires. So on the left hand side you have the height image, and on the right hand side you have the EFM amplitude image. If you happen to take a look at the height image, then what we find is that these nanowires, they are not much distinguishable in your height image. So if you happen to take a look at this region right here, then you actually cannot see any nanowire. But if you apply a DC bias to such a sample, then what we can really find is that Now, these nanowires or these PT coated nanowires, they have got higher surface charging, okay, and they are clearly visible in your EFM amplitude image, okay, as compared to your height image of that particular sample. So here you find that these nanowires are now clearly visible, which were not visible in your height image. There is this another example which is given by this standard sample. So this blue electrodes are nothing but these golden electrodes or these golden patterns which are on your silicon oxide surface or substrate. So these blue patterns are your grounded lines, right? And the opposite electrodes are your biasing lines. Now, if you happen to take the height image of this particular, of these particular golden electrodes, right? Then the height image is given by the top figure right here, where you have these alternate ground and bias lines. The same can be revealed in your line profile, where these ground lines and bias lines are clearly visible and clearly distinguishable. However, what we can do here is that we can apply a sample bias of, let's say, around 0.5 volts in this case, right here. And then we find that the EFM signals between the grounded and the bias electrodes are clearly distinguishable, okay, when you take a look at the EFM amplitude image and the EFM phase image. So this middle image right here is your EFM amplitude image, and the bottom image is your EFM phase image, where you can clearly find out, the bias lines, okay, as well as the grounded lines in case of this particular experiment which was performed. In EFM, there is another very important mode which is called as Kelvin Probe microscopy. And this Kelvin Probe microscopy is governed by this equation number 3. So whenever you take a look at or expand that equation number 1, then the second term which pops out is given by this equation number 3 in this particular case, which we use it for Kelvin Probe microscopy. What we really find here is that the electrostatic force in this case is mapped at a frequency which is given by omega tip, and this frequency omega tip is nothing but it is the frequency of your AC sinusoidal voltage, which was applied to your tip. And what we do is, there is a second lock-in amplifier which locks in at this particular frequency omega tip to reveal the electrostatic force. Now, what is done additionally in this case is that, if you happen to take a look at equation number 3, then we have this term which is VDC minus VS. Now, in this case, if this bias voltage VDC becomes equal to your surface potential, then the electrostatic force, goes down to 0. Okay. So whenever we perform this Kelvin probe microscopy experiment, then what we do is at every point or at every pixel of your sample surface or the image, what we try to do is we try to use a DC bias feedback, right? So in this case, what we do is we sweep this DC bias in such a way that this DC bias becomes equal to your surface potential, and your electrostatic force at the frequency omega tip goes down to 0. And this is what we want. So whenever the force goes down to 0, we map that DC bias at every point or at every pixel of your image, and then you get a complete image where you have the DC bias that had been applied, where the electrostatic force went down to zero. And that entire map of this VDC is then nothing but it is going to be a map of your actual surface potential of your sample surface. So, just by sweeping this DC bias, we are in a position to map or map quantitatively what is the surface potential of your sample. Kelvin Probe microscope, it not only measures, quantitatively what is the surface potential, but, it also can give you the absolute values for the work function of your sample surface as well. There is a nice example where we use HOPG surface, and the top image is the height image of your HOPG, and the bottom image is your surface potential image of that particular sample. So what we do in this particular case is that, while we are scanning the HOPG surface, what we do is we apply stepwise sample bias of 1 volt, 2 volt, 3 volt, 0 volt, and -2 volt. Now, by applying this bias, it doesn't really, display any change to the height image, but as you sweep or change this sample bias, this particular change of the sample bias or the surface potential, gets reflected in your KPM channel itself, and it then reveals, how the sample bias was changed, and what is the sample potential at every point or at every pixel of that particular image. Now, in this case, since initially we applied 1 volt to the sample surface or the sample bias, then this KPM signal or KPM channel actually gave you that 1 volt, which is revealed in this line profile. So if you take the line profile, then it actually reveals that 1 volt. Then the moment you change it to 2 volt, the KPM channel, revealed that 2 volt as well as your surface potential. And then as we changed it to 3 volt, the KPM channel, reflects that 3 volts in its image, so on and so forth. So KPM, not only, gives you how the surface potential looks like, but it actually quantitatively gives you what is the surface potential of your sample. This is the schematic diagram for the KPFM experiment that we do. So in this case, the first lock-in amplifier locks in at a frequency of cantilever resonant frequency omega naught, and the feedback loop then reveals the topography of the sample. Now what we do is we apply a AC bias with a frequency omega tip along with the DC voltage, and then what we can do is we can lock in at a frequency of omega tip using a second lock-in amplifier to reveal what is the surface potential map quantitatively. Now, what we can also do in the experiment is that, using the second lock-in amplifier, we can actually lock in at a frequency of 2 omega. And, the moment you lock in at a frequency of 2 omega, you are in a position to actually map the DC by DZ variation of your sample surface. And this comes into picture, when you take a look at the third term that popped out when you expanded that equation number 1. Now, in this case, what we can do is we can lock in at a frequency of 2 omega, and we find that in this case, this force F2 omega, the DC dependence is actually removed, and the measurement yields the value of DC by DZ map, which is independent of the surface potential, given by equation number 4. From this DC by DZ map, what we can do is we can actually try to derive what is the dielectric constant of the sample itself. Here is one example where, on the left-hand side, you find that, there is this E. coli bacteria, and this is the cross-sectional height profile of this E. coli bacteria. And then on the right-hand side, what we can see is we can see the derived dielectric constant map of that same E. coli bacteria. This you can achieve by simulations and by using simple analytical models, where from the DC by dz map, you are in a position to derive the dielectric constant map of your sample surface. So in summary, I would like to conclude that electrostatic force microscopy is a very popular technique, and it operates in electrical mode in AFM to give you the maps of variations of electric properties of the sample, particularly the surface potential and the surface charge distribution of the sample surface. Thank you very much.